Good morning and welcome back to GIS Day. Today's session is called Geospatial Cloud Data Warehouse Optimization Techniques, brought to you by Ben Scholler and Howell Lee. I'm Jeff Moats. I'm going to be your moderator today. We're going to take questions during this presentation in the chat window. I will read them at the end of the presentation to our presenters, and I encourage everybody to um, enter any questions you may have as they come to you, and we will cover them as we go. All these presentations will be recorded, so feel free to reach back out to the GIO and take a look at this presentation. If the rest of the presentations today are any indication, there is a lot to get through, so I, for one, will certainly be re-examining some of these presentations. That being said, I'd like to get started with Ben Scholler, is a software engineer at Joint Transportation Research Program, or JTRIP. Scholler holds a BS in Computer Information Technology graduate from Purdue University. He primarily works with connected vehicle data and finding ways to display this data in interactive, real-time web applications for use by state DOTs, namely INDOT. Howell Lee is a research analyst at the Joint Transportation Research Program as well. He holds an MS from Purdue University College of Engineering and a BA from New York University in Computer Science. He's got over 16 years of experience in front and back end software development and over 8 years in transportation. Lee currently works in connected, electric and autonomous vehicles, highway mobility, and traffic signal performance measures. His focus is on applying web technologies, big data analytics, efficient data structures, and computing methods to the research and development of safe and efficient transportation systems. Ladies and gentlemen, I will now hand it off to you.
All right, Jeff, just do a quick mic check.
Yes, we can hear you.
Okay. Slides look okay?
Yes, they look great. Go ahead.
Okay. First, thank you for Indiana GIS for inviting us to the GIS Day. And before I begin, I want to thank all of our team members here. It's not just Ben and myself. It's a huge effort on the part of the JTRP team, including our director, Darcy Bullock, full-time staff researchers, and graduate research staff. So I just want to acknowledge them to begin with. And just an overview of the JTRP, who we are. And really, we are a group that sits within the Purdue community on Purdue campus, and we facilitate collaboration between the Indiana Department of Transportation, other higher education institutions, and industry to implement innovations. Just a couple examples, we hold Purdue Road School on Purdue campus every year, usually around March, and we welcome about 3,000 attendees each year. And just to acknowledge where this funding comes from, basically it's a multi-state, it's 11-state pool fund study administered by the Federal Highway Administration. And INDOT is also part of this research project. And the data that we use is from Regional Data Services Incorporated. And here's just a graphic of kind of our hallmark at JTRP of incorporating and facilitating the collaboration between government, academia, and industry. So this is the agenda. We're going to go through some of the background with the data, infrastructure, and methodology, and then getting through some of the detour analysis that Ben's going to talk through, and then get into some of the down the weeds stuff for a little bit, data storage optimization, and then looking at the results. So in the background information, we've been working a lot with connected vehicle data, and kind of our mantra is, our vehicles now know more about our infrastructure and roadways than we do, right? Because we have systems that can tell you how many seconds there are as you pulling up at a traffic signal, a traffic light, how many seconds you have until the beginning of green. We have systems that tell you if there are congestion or incidents ahead, or if there are police vehicles ahead, and so forth. Systems that can detect slippery conditions on the road. And these are all instrumented vehicles with GPS sensors and sensors that track wheel speed and windshield wipers and so forth. All that information, right now, the automotive industry is looking to capitalize and looking to see how we can leverage some of this data. As I mentioned, the connected vehicle data is helping agencies to do things safer, faster, and less expensively. And also, how do we, now that we have potentially billions of data points coming in, right? So these vehicles generate tons of data every second. How do we quickly and inexpensively query the massive amounts of data that are coming in? It's a huge geospatial data problem. And it's a challenge to take all this data, and we're not going to dump 10 billion points on a Google Chrome dashboard, right? That doesn't make any sense. It will take forever to load. And how do we generate those reports that we have those informative and really information and reports that we can use for data-driven decisions? So data overview. The amount of data that we manage at the program, just to give you all a flavor, connected vehicle records, we have over 300 billion records with 11 billion added per month. We also have the segment-based traffic speed, so similar to what you see on a Google Maps, traffic interface where you have segments of roadway. We get about 2.5 billion records per month. We also ingest National Weather Service data at 420 billion records and counting, and also traffic camera images from Indiana DOT. Currently, we have over 120 million images. An additional 15 million images are scraped from snowplows, the dash cams that, as they're going through and plowing and salting the roadways in a winter storm, we get those at 1-minute intervals as well. So a description of the connected vehicle data, what is it, right? So it's anonymized data, and basically it gives us a trajectory of a vehicle in latitude and longitude and a timestamp, speed, and heading, really what a vehicle is as it goes through a state of Indiana. And the precision is 3 meters and 3 seconds temporal fidelity. So let's say you have a Friday afternoon between 4 and 5 p.m., typically a very busy hour. How much data are we looking at here, right? So that velocity of data that's coming in, the volume, right? So it's 100,000 data points in 10 seconds. So the map that you're seeing with the entire Indiana road network lit up, that's 10 seconds of data. And if you look at all the states for the full fund study, the 11 states looking across the country, over a month we have 167 trajectory events for the month of August 2020, and that's about also 103 million heartbreaking and heart acceleration events. So leaving out the latitude, longitude locations every 3 seconds aside, when there is a heart acceleration or heartbreaking event, we also track that. Anything that's over 2.67 meters per second squared is considered heartbreaking or heart acceleration. So with that, I think I'm going to kick it over to Ben Scholler, who will go into the infrastructure methodology and a couple of use cases. So I think he will share the screen. So over to you, Ben.
Fred, you're muted, Ben.
Hi.
Hey, there you are.
Sorry, my mouse cursor has seemingly just disappeared on me. Oh, there it is. Sorry. I am a software engineer here, and I'm going to go over how we use some of this connected vehicle data to help analyze traffic patterns. So our high-level infrastructure that we've got set up right now, we get data from our connected vehicle data provider, and from there it gets ingested and linear referenced, and then put into BigQuery. After that, so BigQuery is a cloud data warehouse that's a part of the Google Cloud Suite. And after that, we run some business logic on it to aggregate some of the data and put it back into BigQuery, again into separate tables. And from there, it is used for ad hoc research queries and also our web dashboards, which we'll get into. So our linear referencing process looks something like this. We first create a buffer around the center line of a road, as you can see here, and then retrieve all the data from within that buffer. And then after that, we match it to points every 100th of a mile along the center line of the road. And that gives us a mile marker, if you will, for where the points are, and allows us to really easily plot it on a 2D Cartesian plane. So one of the main use cases for this for us is detour analysis. So this is a recent crash on I-65 North, where this blue semi you see on the left of the image was carrying two 35,000-pound steel coils on it, which is over the limit. But anyway, they hadn't strapped these coils down, and they came loose during transit and caused a crash. Now, due to the size and the sheer mass of these coils, they had to come out here with plasma cutters to chop up the steel coil to haul it away. They couldn't just pick it up. That said, it caused about a 4-hour closure on the interstate. So with this tool that we have, we can look at the we can look at the traffic and the closure in really fine detail. So on the x-axis here, we have the time of day, and then on the y-axis, we have the mile marker going from balloon A to balloon B. So these lines on the main plot here are colorized by the speed of the vehicles. So pink and purple being 0 to 15 miles an hour, and green being 65, more than 65 miles an hour, so uncongested speeds. At the bottom, we can look at the travel times that these vehicles experience. So as you might expect, the travel times while this accident was going on and while they were cleaning it up peaked quite a lot, up to almost 3 hours. So some of these people were sat on the interstate for 3 hours or trying to find a way out. With this, we can look at the detours that these people took. So you see the pink points jumping around on the travel time plot there. Those points correspond to the pink line on the map. So that's the route that the vehicle actually. And we can see in this case, the vast majority of the vehicles, at least in part, took the official detour on US 52. So another example, there was a crash on 65 where a Mazda Miata traveling southbound bumped into a Chevy Tahoe also traveling southbound, causing the Chevy Tahoe to cross the interstate, go all the way across the median, and crash head-on into a Greyhound bus. According to the news article about this crash, the two people in the Chevy Tahoe died on scene, and many of the almost 50 passengers on the bus were carted off in ambulances to nearby hospitals. So this is one of the worst accidents that we've seen in recent Indiana history. This accident caused nearly a 7-hour delay. We can see here by the white block here where there's no vehicles. And the highest travel time was almost 4 hours. So we can also see a similar pattern to the steel roll crash in this plot, where all these vehicles down below are the ones that took detours, or more so successful detours. And for them, it was mostly less than 90 minutes, which is still not great, but it's better than 4 hours. Additionally, on this plot, there's blue horizontal lines to indicate the interchanges. So in this video, we can see much more creative route taking by these drivers. A lot of these routes cross this State Road 225 bridge, which is a really small one-lane signalized, so a signal at each end. It's a really small bridge across the Wabash, and it has a weight limit of 12 tons. Now, a lot of semis thought it would be a good idea to cross this bridge too, and semis weigh around 40 tons, which is much more than 12. So following this crash, INDOT closed the bridge for comprehensive structural inspection. So this is just one example of how we use this data to help out INDOT. And we can see a lot of these trajectories crossing that bridge right now. So moving on to how do we optimize this? Because we have all this data, billions of records, but how do we make it into something that we can actually use? So without any form of optimization, and querying the entire table just to pull out one small part for one day, it's going to cost about $75, which is, that's a lot of money, especially when you're wanting to do real-time dashboards and stuff like that. So that's using daily partitions, that's without using daily partitions. So the first and probably the easiest way you can optimize your table is by partitioning it into some kind of temporal period. So for us, it made a lot of sense to do daily partitions. So each day has its own partition, as you can see here. So this makes it so that the database only has to look in this one day worth of data, because it knows exactly where that day is at. So it just totally ignores the rest of it and only looks at that one day that you care about. And this gets this example query down to about 20 cents, which is a lot better, 99.7% cheaper, but still a little bit on the pricey side if you're going to be making heavy use of the data. So beyond that, we found that we could cluster it. So partitioning, as I said, is reducing the search of the data. Now clustering is a pretty similar thing, but sort of one step further, like beyond partitioning. And we can utilize both of these to make it so we only have to search for one cluster. And now we're talking about 0.2 of a cent, which is practically nothing. And with costs this low, it's really practical to be able to, just unleash this data to researchers and practitioners and let them go loose without having to worry about huge cloud bills. So what are geohashes? Geohashes are a public domain geocode system invented in 2008 that encodes a lat-long coordinate into a short string of alphanumeric characters. So basically what that amounts to is taking a coordinate and condensing it into some unique string. This algorithm is very lightweight, consisting of relatively simple math, so it doesn't include any geospatial lookups, which are very slow. Because of this, the grids get stretched near the poles, leading to a 5-character geohash in Lafayette covering about 9 miles, as we can see here. Each of these squares is a 5-character geohash. So by employing geohashes as a key to cluster on in our tables, the database can narrow its search down to just this 9 square mile area. So to look at the results we've seen, they're pretty impressive, to say the least. Now, the thing is, they're arbitrary precision, geohashes are. So that means that you can make them any length you want. They're typically, I would say, in my experience, anywhere from 4 to 12 characters, but the ones we're mostly concerned about were 4 to 6. And the results of our tests were that the four character geohashes are really wide area. They cover a wide area, so there's less clusters to search over in the database. However, those clusters are larger, so they cost more to search. So the advantage is speed, but the disadvantage is cost. However, with a 6-character geohash, we're getting smaller, zooming in, if you will. And the advantage with that, of course, is that it's a really fine, precise area that we're searching for. However, there's so many of them that it slows it down some. So in our testing, we found the Goldilocks zone to be 5 characters, just because it's a nice balance between the two. And this of course depends a lot on use case. So if all of your queries are very small areas, then it would make sense to go for a smaller area geohash or a longer geohash. Whereas if you're searching really long routes or really wide geographic areas, it makes more sense to use larger geohashes. And in our tests, we saw a 98.8% decrease in costs, going from about 10 cents to query. And this is already with daily partitioning, this no cluster, down to 1/10 of a cent, so minute costs. So to sum it all up, we use cloud data warehouses to quickly and expensively query connected vehicle data at scale with geospatial functions. And it's taken a lot of optimization to get there, but it's definitely proven itself to be the most practical way to manage this, the sheer quantity of data that we're dealing with. We're ingesting about 1 terabyte of connected vehicle data per month in this state, and 10,000 rows per second, or 10,000 per 10 second, or sorry, 100,000 per 10 seconds in the peak hours. And we can generate these dashboards here in about 20 seconds, with including the query and the linear referencing, the whole thing, for about 1 cent per query for a 20-mile corridor over a day, to look at queuing and detours and that kind of thing. And just to give you an idea of how many points are just on this alone, the steel roll crash, that's 468,000 points, all being plotted in the web browser.
That is remarkable. We're about 10 minutes out for the presentation, so just to give you a heads up.
Yep, well, that's perfect. That's the end. So if anybody has any questions, I'm happy to answer.
Well, I don't see anything in the chat window yet. For those of you who are viewing, I encourage you to type in any questions you may have. Otherwise, we have contact information for Ben and Howell here on the screen.
Crickets.
Crickets, that's good. You left them wowed. No, that's a lot to take in, and that's really a great application of GIS and that big data application that is so often talked about. I sure appreciate everything you guys do. Transportation, usually you only hear about that when things are bad, things are under construction or a detour, but we certainly appreciate the effort you guys are putting into the study. We've got a lot of good presentation got compliments coming in. One question wants to know if is access available for us peons? Ben gets extra credit for the vocabulary word. So the general public, if they were interested, could they get a hold of this data?
So
How
yeah, I can answer that question. So in terms of the raw data, that is we have to license that that data, the raw connected vehicle data. So and that's pertaining to the terms of the contract, and I don't believe we can share that readily. But in terms of the dashboards and the reports and the analytics, we have shared that with the Indiana DOT and other sponsors as well. General public right now, we tend to keep it obscure right now because of the general impact to really the performance and the amount of data. As you know, it's 1 terabyte a month, as Ben has mentioned, just for the state of Indiana. And it's even though he's gotten it down to less than a penny per query, potentially thousands of users hitting it, we have yet to address that magnitude. So stay tuned, though.
Understand. Yeah, those pennies do add up. Another question came in. Again, this was really a deep dive question came in. Are there some resources to help better understand this process? I will reiterate once again, this presentation is being recorded and will be available later, but I'll hand it back to you two if there are more resources available.
Yeah, Ben, do you want to answer that one, or?
Sure, Rick? Are there specific things you're looking for? Help with optimizing the tables or further reading? What kinds of things are you talking about?
Okay. We'll see if he gets a. Yeah, we still got time. We got plenty of time.
Sure. Yeah. I mean, in terms of the Google Cloud Platform BigQuery product, I think background showing up here. So I would say there's a lot of there are a few public freely accessible data sources or data sets that you can kind of play around with on BigQuery. I think if you get like a Google Cloud Computing account, and then you can just activate the BigQuery product. There are a lot of public data sets that you can I think there's a lot of weather, cab data from New York, a couple other data sets that at your disposal that you can run SQL. It's basically SQL queries off of BigQuery. So the transition has been really easy because for us, we went from an on-premise system where we ran Postgres and SQL Server, and we took that whole, the set of queries and dashboards. Really, we pointed everything to BigQuery after we loaded the data, and with minor adjustments like in terms of geography functions, we just changed the names of a few. Everything just worked pretty smoothly in BigQuery. So there's a lot of good documentation out there for Google. Oh yeah, okay, Rick. So I just saw your follow up there. So yeah, so there should be some public data sets on BigQuery that you can kind of exercise and play around with some of the APIs. Ben, is there anything to add on your end?
No, I think that's all I've got. I'll mention how I may be mistaken on this, but I think that there was some query at one point you were trying to run on-prem with our databases that was going to take 30 days. And with the data on Google BigQuery, it was closer to 8 minutes. Am I right with that?
That's right. So that's part of the data ingestion process. As you all know, writing data is always more expensive in terms of time and computational costs. So for us to ingest 1 month of Indiana data using servers that we had, and we had SSDs, we had pretty robust systems, but it was a single node, and it would have taken us 36 days. So more, it would have taken us longer than a month to ingest a month of data. Put it this way. So when everything's done in cloud, nothing comes on-prem. We don't have to transfer the terabytes of data. Ben said, we were able to do that in a couple of minutes. So
That is impressive. I'm a simple man and my head is spinning, so I am really I'm really impressed with the work that's been done here. Any other questions? Again, still got minutes here. For those that have joined today, I invite you tomorrow morning to log in again for the second half of our GIS days, and really some great presentations coming around. So, as usual, I'm encouraged by the excitement, the innovation when we do these presentations. So always excited for GIS making an impact. Hearing none, I will just sign off now. I'll leave everybody here to reach out to the two of you if more questions appear. Otherwise, I want to thank you both for your presentation, and again, thank you for the work that you have done.
Great.
thank you, Jeff. Thanks
Thank
for
you.
having us.
Have a great day.
You too. Thank you.
Bye.